In Lecture 8 of Electrical Fundamentals, we will focus on superposition theorem and circuit analysis. Circuits where you have more than one source. So for example, if you look in this picture here, in this schematic, you have two sources. You have a voltage source and a current source. It doesn't really matter what type of sources, whether they're voltage or current. We will see how to tackle these type of circuits. Superposition theorem can be summed in the following sentence that I wrote to you here. So it is a method for analyzing a circuit that contains two or more sources by examining the effect of each source by itself and then algebraically combining the desired current or voltage results. So one thing to pay attention to is that superposition only works with when you're trying to find a specific current or a specific voltage somewhere in your circuit. It does not work when you want to find the specific power dissipated somewhere in your circuit. So superposition in power are completely no-go. They only work with current and voltages. When you apply superposition, you want to turn off or you want to remove the remaining sources. So let's say if you have a voltage source and you want to remove it, what you do is you replace it by a short circuit. If on the other hand you have a current source, what you do is you open that area. So you open the circuit when you have a current source. That's how you get rid of a current source, and this is how you get rid of a voltage source. So these two are things that you really need to have in your toolkit to remember this. Voltage source, when you want to get rid of it, you short circuit it. Current source, when you want to get rid of it, you open circuit it. And this will be necessary as we solve superposition related problems, circuits with more than one source. We'll do some 5 examples in this lecture, and I think that's the best way to really understand how superposition theorem works. As noted earlier, superposition only works with voltages and currents. So in fact, when you want to find a specific current or a specific voltage, let's say in this circuit, you're looking for I2, the current that flows into resistor 2, you can certainly apply superposition theorem. But the question is, how many circuits do you need to analyze? So the number of circuits that you need to analyze is always equal to the number of sources that you have in your circuit. So if you look in this example, how many sources we have? Well, we have one source here, it's a voltage source, and we have another source here, it's another voltage source. So in essence, we have two sources, and therefore we need to analyze two circuits. If we look at this second example, we also have two sources. We have this source, it's a voltage source. We have this source, this is also another source. However, it's a current source. It doesn't matter if it's a current or a voltage source. At the end of the day, there are two sources, and therefore, again, we need to analyze two circuits. Now, the first circuit will focus on the first source, and the second circuit that we analyze will focus on the second source, and then we combine the results for I2, let's say. Same thing here. If we were to solve this, we will first solve for I2 with the first source, then we will solve for I2 with the second source, and then we combine the result. Let's look at a third example. In this third circuit example, we have three sources, this one, and this one. And therefore, we need to analyze the circuit 3 times. In this fourth example, if you look, we have, again, 3 sources, this one, this one, this one. 2 of them are voltage source. This one is a current source. And what this means is that because we have in example 3 and 4, 3 sources, it means we have to analyze the circuit 3 times. The first circuit will focus only with this, and then we get rid of the other 2. The second circuit will only focus on this current source, and we get rid of the other 2. And the third circuit will only focus on this one, and we get rid of these 2. And the same thing applies to this. So this is kind of in a nutshell, what we mean by superposition, is that we look at the impact of each source on its own, and we try to find whatever we're looking for. So if we're looking for I2, we only look at it with respect to this source. Then we also look at the impact of I2, what I2 is with only this source, and we combine them together. Like I said before, it will make more sense when we solve some problems, and you'll get a sense of how superposition works. If we want to find the power dissipated with a certain component, we cannot use the values of power directly with superposition. What we rather do is essentially find the total current that we're interested using superposition, or the total voltage that we're interested by in the circuit using superposition. And then after that, once we have the total voltage or the total current, or perhaps both, then we could apply a Watt's law and determine the power. We cannot find the power directly with superposition. So in other words, if you find the power with one source, and then you find the power with a different source, and then you add them together, this will give you a wrong answer. So that's essentially what I wrote to you here. Superposition doesn't work by summing the power levels. So this is something to remember. It only works when you sum the voltages and the currents. And we keep kind of stressing this in this lecture and throughout the lecture. So if we, for example, consider the following circuit. If you see here, the circuit, we have two voltage sources, this one here and this one here, and we have a bunch of components that are connected. And we ask you, find the power dissipated by R2. How much power is dissipated by this resistor? And to be honest, we also have another thing that we're interested is to find I2. What is I2? The current that flows into this resistor. So in this case, like we said, one approach one might consider, for example, applying superposition. And through the concept of superposition, we begin by looking at the first voltage source, this one here, and we call this circuit A. So we consider this one here. The other one, we get rid of it. So we put a short circuit for the other one. We get rid of it. So we only have this circuit. And now we could essentially solve for the current that flows into this resistor. Let's call it I2 sub A, and for the voltage that is across this resistor, so V2 sub A. And we apply Watt's law to this, and we determine through Watt's law the three different ways of writing the power equation for this circuit. And then let's say we do it for the next source. So we get rid of this source, we short circuit the source, we keep the other source, and we also write the related equations for Watt's law here. And essentially what we might end up doing is simply add this power to this power. Now this is where people do this mistake. Students do this mistake quite often. They think that superposition applies if you do this. All that I just showed you here, this will give you essentially a misleading answer. So this, the answer that we have here, is absolutely misleading. If you find the power for the first circuit, the first source, and the power for the second circuit with the second source, and adding the power, this will give you a misleading wrong answer. It won't give you the total power dissipated by resistor 2. This is gives you a wrong answer. So in other words, essentially what this means is that superposition really does not work when you work with powers. So if you're interested to find the power dissipated by R2, then what do you do? So what you essentially do is you find the voltages, because voltages work with superposition, or the currents. The current works with superposition. So essentially you consider this circuit, you find I2A and you find V2A, and you work with this circuit, you find I2B and V2B, and then you add them together. Now you have the total voltage and the total current. This works. This is superposition applied to voltages and current. This is correct. And once you have this, then you could apply your Watt's law to it, and this will give you the correct value for power. Whereas if you do this, this will give you the wrong values for power. So this is something to really make sure that you focus on. Is that power does not work with superposition, whereas voltages and current it does, and then you use them with Watt's law to find the total dissipated power. I hope this is clear. We'll see some examples later on, but hopefully this slide gives you a sense of what you should do when you work with powers in superposition and what you shouldn't do. So, like we said, we will solve a bunch of questions to really understand how superposition works. In reality, 5 questions, and this is the first question that we will attempt at solving. This is the circuit that we're giving to you. Right away, without even mentioning the word superposition, you see 2 sources. One source, another source. You know right away the key trick for you to solve the circuit to find your I2 would be to essentially use superposition. So let's go through the steps of what to do. As a first step, I always like to annotate the circuit in order to show the trace for the current, how current flows in the original circuit, the circuit where you have both sources. So let's just do that right now and see how this works. So let's annotate this. If you see, let's do it for the first source. For VS1, it could also be called VSA and VSB, it doesn't really matter. So this side, has a bigger bar, so this is your plus. This has a smaller bar, this will be your minus. This is your plus, this is your minus. And current will flow like this. It leaves the source, it goes into R1, it moves up to this point, it leaves this source, it goes in here, it goes into R3, it comes to this point, it merges together, it goes into R2. At this point it is split, part of it will go here, and the remaining part will go to the source here. And this is how we do the trace for the current when you have multiple sources. And if you notice the direction for I2, we really expect it to be flowing downward toward like this, right, as shown here in the picture. So the blue line here, this is the correct direction for I2. This is what we expect. So as a first thing, we will consider this one, this source, we'll call it circuit A, and we will consider this one and we'll call it circuit B later on. So in order to do this, let's consider circuit A. And this is our circuit A. If you notice, we keep the source and we get rid of the other source, the second source. And when we get rid of the other source, we essentially just put a short circuit in here. And this is how the other source is gone. At this point, we want to find this I2A. And in order to find I2A, what we need to do, in fact, we will call it I2 sub A because we're solving it for this circuit. And it's always a good practice to annotate your circuit and your variables in a correct way. So this is a sub. This is not I2. If you write I2, you might do a mistake later on. So this is, you're doing it really for circuit A. This is not the total I2. This is only for circuit A. And this is what we're after in here. So as a second thing that we could do is essentially annotate this circuit. And so it's no longer, don't look at this circuit anymore. This is done. We're done with this. We only focus on this. From now on until we finish this, we only focus on this circuit. And this is where we need to pay our attention to. So let's annotate this circuit A and see how everything moves and flows in here. So if we notice here, this is the bigger bar. So this will be the plus. This will be the minus. Current will flow like this into R1. It moves, it comes here. Part of it will go into resistor 2. The other part will go into resistor 3. It merges again, and it goes back again to the source. Okay, so now in order to find our I2A, because this is what we're after, we want to find this thing here. This is what we want to know what it is. What we could do is we could use some of the tricks that we've learned in previous lectures. So essentially KVL, KCL, Watt's law, not Watt's law, but KCL, KVL, Ohm's law, voltage divider rule, and current divider rule to see how we could maneuver and find our I2A. So let's do this. As a first step, we'll find the total resistance of this circuit. The total resistance is R2 and R3 in parallel, and they are added to R1, and that gives us the total resistance for this circuit. So we could call it RTA or RT1, doesn't really matter as long as we know it's not the total for the entire circuit, it's only for circuit A. So let's plug in the values. So this is 2.7, 6.8 for R2, and 6.8 for R3. Without doing any math, it's going to be half of this because they're similar. So it's going to be 3.4 plus 2.7. So this is 6.1 kilo ohm. So the total resistance of circuit A is 6.1 kilo ohm. The second thing that we could do is we could find the total current that leaves this circuit. So in other words, the total current is really here, right? So this is our total current. It leaves this source. So let's call it ITA or IT2, IT1 rather, sorry, or ITA if you will. This is what IT1 is, the total current of circuit A. So essentially what we do is it's really the voltage source, the 12 volts, divided by the total resistance, so 12 divided by 6.1, and that gives us 1.97 milliamps. So now we have 1.97 milliamps, and this 1.97 milliamps is split between two branches. Part of it will go to this branch, and the other part will go to this branch. In order to find the one that goes into this branch, we could just use the current divider rule. So in order to find I2A, we just use IT1, which is our 1.97 that we got, and we find the total resistance of these two, R2 and R3. So putting them together, so R2 in parallel with R3, and in the bottom we put R2. Plug in the value, so 6.8 in parallel with 6.8 divided by 6.8. And that gives us 1.97, 3.4, because it's simply half divided by 6.8. That's only 2. And we determined that I2A is 0.985 milliamps. So at this point, we got what we want, right? For circuit A. We're not done yet. We only solved it for this circuit. Then we have to solve it for the other circuit. And then we combine the result. But it is always a good practice to create like a summary section for your analysis. And it will make more sense when we go to the next slide, how this summary section is useful. So I'm going to just put the summary of what we found in here. And what we found is 0.985 milliamps. And if you notice, it is moving downward. Getting the direction correct is also useful and very critical when you work with superposition. So at this point, through the analysis of the first source, we determined the contribution to I2 from the first source to be this, and it's going downward. So at this point, we could focus on the second source and eliminate the first source. So let's show you the circuit. This is what we have for the circuit. And what we could do is we could essentially annotate the circuit in order to better understand the flow of the current. So this is the plus, this is the minus. As you notice, we got rid of this source, so that's why we put a short circuit here. And we kept this one, and this is how we get circuit B. With the current flows from the plus, it goes into resistor R3. It comes to this junction. Part of it is split. It goes here. The other part goes to resistor R2. It moves like this. It moves, it comes to this junction, it joins together, and it goes back again to the source. Okay, and at this point, with the trace of the current, we get a better understanding of how the direction of I2B should be, and in fact, it should be pointing downward. And now we're really looking for this, what this value is. What is I2B? What is this? This is what we want to find. So we could apply the same approach that we applied with circuit B. And what we could do is we could find the total resistance for this circuit, for circuit B. So to do that, we show you the steps here. So essentially, simply by looking at it, you know that R1 and R2 are in parallel, right? And then the result that you get, you add to R3. So R1 is 2.7, R2 is 6.8, and the result that we get, we add it to 6.8. And then we do the math. So it's 2.7 times 6.8, 2.7 plus 6.8 plus 6.8. We do all that, and we determine that the total resistance for this circuit, for circuit B, is 8.73 kilo ohm. Okay, so we obtain this. The second step that we do is we find the total current flowing out of this source. So for this, we could essentially use Ohm's law to determine this, and through Ohm's law, we determine that the current that flows out of the source is 2.06 milliamps. Okay, so we have 2.06 milliamps. This 2.06 milliamps, part of it will flow in here through this resistor, and the other part will flow to resistor R1. So therefore, we could, in fact, use the current divider rule to determine what is the component that flows into resistor 2, and we call this I2B. Okay, so we use the current divider rule. Sorry, and this gives us that I2 T2, which is 2.06, and we do a ratio of a small value of R1 in parallel with R2. So this is 2.7 in parallel with 6.8 divided by the resistor R2, 6.8. So we enter the value, do the math, and figure out that the current that flows into R2 is in fact 0.585 milliamps. Again, in here, we need to then continue putting our data in the summary table. The summary table is critical when you do superposition, like I mentioned before. So we entered what we got here for I2B. We got 0.585 milliamps, also flowing downward. And now when you want to find the total current for I2, you simply add them together. They're both flowing downward, so you can simply add them together. And if you, this addition, when you add them together, this is called superposition. You add them together, and we determined that it is 1.57 milliamps flowing downward. And we got the answer. So this is really the answer that we were after all this time. So this result, this 1.57, is in fact what this value is. This is 1.57 milliamps. And if you notice, this is how superposition works, right? So we do it for the first source, we get the result. We do it for the second source, we get the result, and then we add them together, and we get the final result for whatever current or voltage we're looking for. So that completes the first question, and now let's move on to the second question. In question number 2, we are given this circuit. We have two sources, source A, source B, and we're looking for the current I3 that flows here. As a first step, it's always good to annotate the circuit. So we can do this right now. We have the plus in here, we have the minus in here, the plus in here, the minus in here. The current will flow like this into resistor R1. It will come here. It will flow out of resistor, out of the source into this point. At this junction, it will go into R2. It will come here. Part of it will go into resistor 3, like this. The other part will go into this path toward the first source. So now that we have this, we kind of have an idea that the current I3 will in fact flow in this direction, like this, in this path. So now what we could do is the following. We could focus on circuit A. Circuit A will be based on this source, VS1, and circuit B will be based on this source here. So let's focus on circuit A and see what we get. So for circuit A, we keep the source A and we get rid of source B. We simply short circuit source B. And this is what we get. We have our 54 volts. We have resistor R1. We have resistor R2. And we have a short circuit here for resistor R3. And we are curious to know what this current is. Current I3A is the current that flows into resistor 3. So if we do the trace for this circuit, this is what we get. This is what we get. So this is the plus, this is the minus. Current will flow into resistor 1. It comes here. It flows into resistor 2. It goes in here. It comes this way. It merges together. And it goes into the source in here. So if we have the circuit, we could find the total resistance. And the total resistance is nothing else but R2 and R3 in parallel. And the result that we get is added to R1. So if we do this, this is what we get. We get R2 in parallel with R3, and the result that we get is added to R1. And therefore, we get 12 in parallel with 4. And the result is added to 24. So that gives us 12 times 4 divided by 12 plus 4. And that gives us 3. We add 24 to it, and that gives us 27 ohms. Okay. So now that we have the total resistance for this circuit, we can find the current that flows out of this circuit. So the current that flows out of this circuit is here. So it is here. This is the current that flows out of the circuit. So let's call it T1. And the total current that flows out of the circuit can be determined as follows. So it's really the source, the 54 volts, and the total resistance, the 27 ohms, and that gives us 2 amps. So we have 2 amps that comes here. Part of the 2 amps will go into resistor 2, and the remaining part will go into resistor 3. So let's just write it in here. So this is equal to 2 amps. Part of it will flow here, and the remaining part will flow in here, and that gives us basically our I3A. So we could find the current I3A by simply applying a current divider rule, and this is what we get. So the current is really the 2 amps that we got, and we have 12 ohm in parallel with 4. And in the bottom, we simply put the 4 amps, and 12 in parallel with 4, we already determined this. This is 3. And in the bottom, we have 4, so that's 6 divided by 4, and that gives us 1.5 amps flowing like this, flowing to the left. So 1.5 amps flowing to the left using the same convention. So we're looking at it on this line here, and therefore it's flowing this way, flowing to the left. And we note it in the table that we have for the summary. Okay, so now we continue and we look at this source and we eliminate the first source. So this one becomes a short circuit, and we only look at the second source, source B, or if you will, VS2. So if we do this, this is the circuit that we get. We have the source, and we essentially have it as such. We have resistor 1, we have resistor 2, and we have resistor 3. And the plus is on top, the minus is in the bottom. And we could certainly annotate this and determine the R total. So let's do the annotation of this circuit B. This is the plus, this is the minus. It flows like this. It comes as such. It comes down like this. It merges. And it goes again together to R3 and back to the source. So it's really R2 and R1 that are in parallel, and then we add R3 to it. So R1 and R2 in parallel, we add R3 to it, and that's 24 in parallel with 12. We add 4 to it. That gives us 12 times 24 times 12, and 24 plus 12 plus 4. This becomes 8 plus 4, and therefore we get 12 ohms for the total resistance of circuit B. At this point, what we could do is we could find the total current, and the total current is in fact obtained using Ohm's law, so which is basically just our 48 volts. And the total resistance is 12. So 48 divided by 12, that gives us our 4 amps. And this is really enough. We don't need to do anything else. This 4 amps is what we have here. So it is what we have here. This is the 4 amps that we get. 4 amps is here. And in fact, this is also the 4 amps that is here. It comes back again in here. Therefore, I3B is really equal to 4 amps. So we really solved it for I3B, and now we have the answer. So it is really 4 amps flowing to the left. And if we note it, it's 4 amps and it's flowing to the left, and that's what we get in here. So if we apply superposition, we have in the first circuit a 1.5 flowing to the right, and in circuit B we have 4 amps flowing sorry about that. We have in circuit B 4 amps flowing to the right, and in circuit A we have 1.5 amps flowing to the left. And if we do the resultant of both, the total current will flow to the right by doing 4 minus 1.5, so 4 minus 1.5, and we'll get a resultant current flow of 2.5 amps flowing to the right. And this is the final answer that we get. Okay, question number 3, we have the following circuit. So as you see, we have 2 sources, source VS1 and source VS2. We could also call it source VSA and source VSB. It doesn't really matter, just 2 sources. Here, be careful with the sources. This one has the polarity just like we've seen before, the plus on top, the minus in the bottom, and also you have your ground here. This is your reference point, whereas this one is flipped. So here, be careful. This is sometimes used by instructors to kind of trick students and see how they react to these kind of changes in a circuit. So the minus is on top, the plus is in the bottom. So you have to be careful. And it's a 48 volt source. So, and we're really interested to know what R2 is, the value for the current R2, and also the direction of it. So we want to find I2. This is the question. So I think as a first step, it's not a bad idea to do the trace for this circuit. So let's begin by doing this with the original circuit with the both sources being connected. So again, let's maybe annotate that this is source A, this is source B, and therefore we will have two circuits that we need to analyze. This is the plus here, and this is the minus here. This is the minus, and this is the plus. So here, be careful, it's flipped. Current flow goes out of the plus. It goes into resistor 1. It reaches this junction. Current goes from the plus. It leaves the plus. It comes here, okay? At this point, because it's negative, we expect the current to come back to it. So we expect the current to go like this, to go back to it. So I guess part of it will go into resistor 3, the current from source A, and the other part will go into resistor R2. So it comes here. These two are merged together. I2 with the current from this source are merged together, and they go back again to the source A. And you notice that this is how we figured out the flow for the current, the trace for the current when both sources are connected. So now that we have a sense of the direction of I2, we expect it to be flowing downward. Although we cannot say fully that this is the case because the value of will play a role, but this is kind of in general how we expect the current I2 to be flowing downward. The analysis will lead us to whether this is correct or not. So now let's analyze circuit A. For circuit A, we keep this source and we get rid of the other source. To get rid of the other source, to remove it, we short circuit this one here. So if we do that, this is the result that we get. We get the source for circuit A. We get the first source. We have our 3 resistors, and this one is simply replaced by a short circuit. And this current is now denoted as I2A because we're solving for circuit A. So now that we have this circuit, let's annotate the circuit and show the trace for the current for this one, for circuit A, without the other source. Because it does not guarantee that it's going to look exactly like this one. It's unique, and we need to really do the trace for this one to get a sense of how the current is flowing. So let's do this right now. Again, we have our source. We have the plus here. We have the minus here. The plus, the current leaves the source. It goes into resistor 1. It reaches here. Part of it will go into resistor 3, and it comes here. The other part will go into resistor 2, and they're joined together, and then it goes back again into the negative side of your source. So this kind of gives us a sense of the flow for the current. Now that we have this, we need some inkling to figure out what I2 is. And therefore, what we could do is it's not a bad idea to figure out what is the total resistance. For the total resistance, we could right away identify that it's really R2 with R3 in parallel, and then the result that you get is added to R1. So R2 into R3 in parallel, we add to R1. So let's just plug in some values. So this is 24, this is 12, and this is 4. So 12 and 4 is 12 times 4, 12 plus 4, plus 24. And this part here reduces to 3. This is 24. And in total, we get a 27 amps for our total for this circuit. The next thing that we could do is we could figure out what is the total current that is flowing here. The total current that is flowing out of the source, it's really the voltage source, which is the 54 volts, and we divide by the total resistance, which is 27, which is in essence 2 amps. So this path here, the current that flows here, it's 2 amps. We could perhaps do the annotation just to give us a visual support. So here, the current here, it's 2 amps. And therefore, this part here is really 2 amps. Part of the 2 amps will go here, and the other part of the 2 amps will go into resistor R3. So we are curious to know what this is, this part, and we could simply use the current divider rule to figure out what is this I2A. So I2A is equal to I total 1, which is our 2 amps. And we do R2 and R3 in parallel on top. And in the bottom, we do R divided by R2. So this is 12 in parallel with 4. And in the bottom, we have 12. If we put in the values together, we get the 2 here. 12 in parallel with 4, well, we got it earlier. 12 in parallel with 4 is nothing else but 3. So it's 3. And in the bottom, we have 12. So that's 6 divided by 12, which is 0.5 amps. So we could put it in the summary table for the circuit A is 0.5 amps flowing downward. Okay, so now we move to circuit B by only looking at this source and eliminating VS1. So to eliminate VS1, this is becomes a short circuit, and we only look at this one here. So if we do that, this is the result that we get for circuit B. We have the source VS2 and VS1. As we said, there's a short circuit here. We could annotate this circuit B. So let's do this. We have the plus in here, we have the minus, it flows like this, current will come here, it will go into resistor R2, it will go into resistor R1, it merges, goes to resistor R3, and it goes back again to the source. So now with this annotated as such, we notice that we have resistor R1 and resistor R2 that are in parallel, and the result that we get is added to resistor R3. So let's just do this. This is what we get. We get R1 in parallel with R2, and we add it to R3, and that becomes 24 in parallel with 12, and we add it to 4, and therefore that's 24 times 4, 24 plus 4, 24 times 12, 24 plus 12. We do the ratio, we add 4 to it, and that becomes 12 ohms. That's the total resistance of circuit B. So now that we have the total resistance, we have the total voltage, we can determine the total current that flows out of this VS2, and this can be done using Ohm's law. So if we use Ohm's law, we have 48 volts, we divided it by 12, and that gives us 4 amps. So the current here that flows in here, it's really 4 amps. Maybe we could put it just so that it is easier to comprehend visually. This current here that comes out of the source, it's 4 amps. And the current that goes back again to the source is, again, 4 amps. Okay, this is 4 amps. So now that we have 4 amps, part of the 4 amps will go into R2, and the remaining part of the 4 amps will go into resistor R1. We want to know the part that goes into R2, and this will give us this value that we're after, I2B. So for this, we could apply the current divider rule. And if we do apply the current divider rule, this is what we get. We get the 4 amps. And on top we do the 24 in parallel with 12, and in the bottom we divide it by 12, and that becomes 24 in parallel with 12. That becomes 8 because we got it earlier. 24 in parallel with 12, we got 8. We divide by 12 and we multiply by 4, and that gives us 2.67 amps flowing upward, and therefore in the table we will write 2.67 with flowing upward, with an arrow pointing upward, and that's what we have. Now we could apply superposition. We have 2.67 amps up, and we have 0.5 amps going down. If you look at the resultant of both, the bigger value, it's the total, the overall current will go with the direction of the bigger value. So it's going to eventually go upward by 2.67 minus 0.5. And this is basically what superposition tells us. So it will go upward by 2.17 amps. And this is the final result that we got for question 3. Question number 4, we are given the following circuit. If you notice this circuit, we have two sources. We have a voltage source and we have a current source. And we're asking in the question to find I0. So I0 is the current that goes into resistor R0, which is 6 ohms. So again, we have two sources. So we first analyze circuit A and then analyze circuit B. Circuit A is this one. Circuit B will focus on this one, and then we get rid of the remaining one. So let's just do this. Circuit A, we will focus on the voltage source, on this one here, the 30 volts, and we get rid of this one. So in order to eliminate the current source, what we do is we open circuit. Because this is a current source, we open circuit this component here. Therefore, it's going to just be two wires that are not connected. It's just air in here, so they're not connected. So essentially we get this circuit that we have in front of us. It's a basic, very simple circuit. We have the plus in here, we have the minus, the current flows like this, it goes in here into resistor R0 and back again to the source. So it's just one loop circuit, so it's a straightforward circuit. And we are interested to know what I and not 0 is, this one here. So we have the voltage, we have the resistance. The same voltage will be here. If it's 30 volts, this will also be 30 volts. Okay, so we have the voltage, we have the resistance, we just want the current. Therefore, we could simply use Ohm's law to do this, and this is very straightforward. So through Ohm's law, we know that I naught 0, because it's for the first source, circuit A, I naught A rather, for the circuit A, is equal to the voltage, Vs, which is 30 volts, over R naught, which is 6, and we get 5 amps for the current that flows into R naught for circuit A. Now let's just analyze the second circuit. For the second circuit, we look at the current source, and this one here, and we get rid of the voltage source. To get rid of the voltage source, we short circuit this. So if we create a short circuit here, and we have our current source, this is a short circuit, so it's going to be a straight wire connected to a current source. Therefore, it's going to short circuit even the current source. So in essence, what we will get is we will just get something like this, right? So, and if you notice this, because this is a wire, it's going to short circuit this. The current source is going to be just a wire connected to a resistor. So it's going to be just R0 connected to a wire to the ground. And therefore, there won't be any current. The current I naught B will simply be 0. There's not going to be any current. So now we also put it in the summary table. We get a 0. 0 has no direction. It's not going up, down, left, or right. And therefore, the total of these two together, of which we got in circuit A and circuit B, is nothing else but 5 amps pointing downward. Finally, we have question 5 with the following circuit. We have two sources, one voltage source of 36 volts DC, and we have a current source of 9 amps, and we have two components, R1 and R2, and we're interested to know the current that flows into resistor 2 in this direction, flowing downward. So we could certainly annotate the circuit. If we do this with the two sources connected together, we have the plus in here, we have the minus in here. This is flowing like this, the current flowing like this. Therefore, this is the plus here, the minus is here. Current will go like this. It goes into resistor 1. It reaches this junction. Current from the other source comes like this. It comes to this point. It merges together. It goes into resistor 2. It comes here, and then it is split. Part of it will come here. Part of it will go back to the current source. And we get the following. So this is always a good practice to do the trace for the current, and therefore this direction that we have for I2 is correct. We expect the current to be in I2 to be flowing downward for the joint sources. So now let's look at source A, this one here, and then we'll once we do that, we'll look into source B, which is this one here. So for source A, we could draw the circuit. The circuit is straightforward, so we keep the source, we keep the two resistors. However, this is an open circuit. It's just an open circuit, so therefore there's nothing, right? So if you will, I mean, we could still draw it just to make sure that everybody understands what's going on. So it's really this what is happening here. So just give me a moment. So it's really a wire that is like this. That is like this. Therefore, because we make the current source open, therefore this is just a useless wire, and we could completely remove it. There's no benefit to having it. So now we have this circuit A, and we need to find the following current I2 A, because it's the A circuit that we're solving, the first circuit that we're solving, flowing into this resistor. So we could use Ohm's law by combining R1 and R2 together. So we could kind of skip some steps here by doing it straightforward. So we have the voltage. We know it's going to be 36 volts for both of them together. And we know the joint resistors because they're connected in series. We could just simply add them together, R1 and R2. So that's 12 plus 6. So it's going to be 36 over 18, and that gives us a 2 amps. So the current here, I2A, is really 2 amps. We could put it in the summary table, 2 amps pointing downward. The next thing that we could do is we could look at source B, this one here, and we could get rid of source A. To get rid of source A, this will be short-circuited, and that's it. So essentially, we'll have just a 2-loop circuit. Right, so this is the source A is short-circuited, and we have the key current source, and we have our 2 resistors. And now we want the current that flows into resistor 2, which we denote as I2B because it's for the Bth circuit. So how do we find this current? Well, this is right away you could use a current divider rule. You know the current here, the current that flows in here is 9 amps. Part of it will go to this, part of it will go to R1. So we could right away use the current divider rule. If you will, if somebody is interested, we could also kind of show you what happens for the flow for the current, the trace for the current. It leaves the current source, it comes here. We have here our 9 amps. Part of the 9 amps comes here. The other part of the 9 amps goes into this path. It merges back again, and then we get the 9 amps back again in here. So we're curious to know what this is. And to do this, we can simply use the current divider rule. And if we use the current divider rule, this is just straightforward. So in essence, we want to find this current. We use the total current, which is the 9 amps. And we take R1 and R2 in parallel. We put it on top. And in the bottom, we just put R2. So this is 12 in parallel with 6. And in the bottom, we have 6. So that's, well, you could simply do this separately. So it's really 12 times 6 divided by 12 plus 6. And then we have 9 over 6. 9 over 6 is nothing else but 3 over 2. So 12 times 6 divided by 12 plus 6, and then you multiply by 3 over 2, we eventually get 6 amps. So the current here is really 6 amps flowing downward. So we put it in the table, and in reality, we could, this table helps us to get the superposition, which is just simply the addition of both, which is nothing else but 8 amps flowing downward. So that kind of gives us the answer that we wanted, which is this. Now, we also wanted to know what is the power dissipated by resistor 2, and like we discussed before in this lecture, we cannot find the power of circuit A and power of circuit B and add them together. That will give us the wrong answer. So what we rather do is in fact get the total current, and from this apply the Watt's law to this current, to this total current of 8 amps. So if we do that, we apply a Watt's law. As we know, there are 3 different ways to use Watt's law. P is equal to VI, P is equal to V squared divided by R, and P is equal to I squared times R. We have the current, so we could use something with current, and we have the resistance. It's 6 amps, so we could simply do that. You take the current, square it times 6, and that gives us 384 watts. That's it. That completes the lecture. Thank you for your attention.